Hello, everyone. Welcome to today's Quantum Spacetime seminar. Today, we are very happy to have Robert Myers from Perimeter Institute, and he would be telling us about complexity and how complexity is equal to anything squared. Over to you, Robert.
Okay, thank you very much. It's a pleasure to be here. I guess these are trying times. I hope we're all staying safe and healthy. But I'm happy to be able to tell you about some work that or a paper that we finished recently before Christmas. And I had the opportunity to work with these very smart people down here at the bottom of the screen. And there'll be a longer paper hopefully coming out in a few weeks. We'll see. In any event, I'm going to start with one of my favorite slides, which is actually holographic entanglement entropy. And if you have seen any of my talks in the past while, you'll know that this has been a focus of something I've done a lot of thinking about. And it was a really remarkable result that, we could relate entanglement entropy in the boundary theory to some simple geometric formula in the bulk. And that idea really became the forum for a discussion or a dialogue where we learned both new things about the quantum field theory in the boundary, but also we started learning lessons about quantum gravity in the bulk. And it gave rise to the slogan that space-time geometry was equal to entanglement, or expressing the idea that entanglement was a key concept in the quantum theory of this emergence of space-time in our ADS CFT. However, Lenny came along, now quite a few years ago, and told us that entanglement is not enough, writing a provocative title. But what he really meant was entanglement entropy was not enough. And he was really pointing out that entanglement entropy is just one diagnostic of the entanglement structure of a state. And we should think more broadly to think about other diagnostics or other ways to understand the entanglement structure of quantum states in holography. And in particular, what he was interested in was trying to understand the emergence of space-time behind a black hole horizon, or how you describe the geometry or physics behind black hole horizons. And now I've been somewhat, I presented this is a nice picture. We all know this is what black holes look like due to the marvelous work of the Event Horizon Telescope collaboration. But of course, in today's talk, instead, I'm going to be showing you Penrose diagrams like this. And what Lenny was interested in is what kinds of diagnostics do we have that can tell us about this region behind black hole horizons? And just to illustrate the point that entanglement entropy was not enough, we can look at a study or a thought experiment done by Hartman and Maldacena. And what they considered was a black hole like this, and they wanted to know what's the entanglement entropy of a subset of the degrees of freedom. But the degrees of freedom they took were an interval on one asymptotic boundary associated with one of the CFTs, and then an identical interval on the opposite side or associated with the thermofield double. And at early stages in the evolution, or if I evaluate the entanglement entropy on say the t equals 0 slice here, what I find is that the Ryu-Takanagi surfaces actually stretch all the way across the Einstein-Rosen bridge. And the surface has two components, and they connect the opposite sides of our eternal black hole geometry. Now, if I push the state to a later time slice, so I'm pushing A and A prime up on both sides of the black hole, In fact, that kind of Ryu-Takanagi surface persists, and now it's probing slightly this region behind the black hole horizon, or in my tube here, or in this tubular region here on this diagram of the time slice. However, if I go much farther, what happens is there's a transition, sometimes we call it a phase transition, where the Ryu-Takanagi surface snaps back, and there has now again two components, but each of the components is entirely in the exterior region of the black hole. And this happens on the typical thermal scales of the problem. And it's something that we should have expected because it's enforced by subadditivity. The entanglement entropy of our system A plus A prime can't exceed the entanglement entropies of the individual regions. And that's precisely what these surfaces are giving us. If I just considered A, the Ryu-Takanagi surface would be this blue surface here. And so the result that it gives us is the entanglement entropy associated just with that region. And so in this regime, in fact, I'm saturating this inequality, and the total entanglement entropy is just the sum of the two. And we can proceed further and further, but there's no change. And in fact, the entanglement entropy is now a constant after that point. And so one of the things that Lenny pointed out is, well, the entanglement entropy, one of the nice things about it is when I think about a reduced density matrix, it's a function of the eigenvalues of that reduced density matrix. But what we would like, or what he suggested we needed, was something that was a more sensitive probe of the density matrix, and for example, was sensitive, say, to the phases in our thermofield double state as we evolve it forward in time. So his suggestion was, well, we should think about complexity, or in this context, holographic complexity. But that's not necessarily a familiar concept. And so I'll just take a moment to review what is complexity. Well, it's what it sounds like. It's really the question of how difficult is it to implement a particular task. And so for us, the question is, how difficult is it to prepare a particular quantum state? And we're going to do this, or we're going to model this task using a quantum circuit model. And so here I have a reference state, which I've referred to as a simple reference state. If we have a string of qubits, they might all, or spins, they might all be in the spin down state. Simplicity, though, is in the eye of the beholder. In the present context, it's really thought that because what we're interested in is in the entanglement structure of the state, that we should start in this process with an unentangled reference state. And then what we have to do here is we have to build up a unitary that's going to take this reference state to the desired quantum state that we're interested in. And how are we going to do that? Well, we're going to introduce a set of unitary gates that act on a small number of degrees of freedom. But the idea is that it's a universal gate set. And so that by acting enough times with these elementary gates, I can take this reference state into whatever state I would like to create on the other side. And so the idea is that we build this big unitary by putting together these elementary gates in a particular way, or in other words, we build a circuit that takes us from whatever our reference state is to whatever the desired final state or target state is. Now, if we're actually working with discrete gates, sometimes it's very difficult to get to the precise target state that we're interested in. And so often what's done is you introduce a tolerance. So you have some measure that of closeness by which we can say that if the state that we produce here is close enough to our target state, say within some tolerance here, then the task has been implemented successfully and we declare success. Complexity then is, well, what we should do is we should think about all of the different ways to build our unitary circuit and find the minimal or the optimal way. And then what we do is we just, in that optimal circuit with the minimal number of gates, what we do is we count up the gates. And that's a number then that we characterize the complexity of our state with. And this is something that the condensed matter physicists have thought about, in particular for topological states or phases of matter. And they talk about there the circuit depth of a particular state. But they're really talking about I mean, it's a slightly different language, slightly different context, but it's really the same idea that we've got here. Just to point out some things that may differ from what you read about, say, in a computer science book. You know, here when I'm implementing my task, I'm starting with a very special input or a single input. Often when the computer scientists talk about complexity, they talk about a problem like factoring numbers. And so the idea is that they'll have many different inputs. And the question is, for a given input, I want a desired output. Here we're starting with a particular input that's fixed. And then what we're going to do is we're going to compare many different states final states, target states. And it's really in that comparison of the final states that we're understanding, or that this complexity is giving us a useful diagnostic. Yeah, that's just what I said. Another comment here that's important is that, you know, I'm in this slide, I'm trying to describe complexity, but I'm doing it in a very abstract way. And I talked about different choices that I had to make. I chose a reference state. I chose a set of elementary gates. I chose a tolerance. And so a natural question is, you know, does the answer I get, does this complexity that I define as the minimal number of gates depend on all of those choices? And of course, the answer is yes. Making different choices, you get different numbers there. And so we really have to think about this in a different kind of a context where, or part of what we have to understand are what are interesting questions where the complexity is giving us a robust answer. You know, what are universal characteristics of the complexity by which I can distinguish different states or different kinds of physical phenomena?
So, sorry, Rob, to interrupt you.
Sure.
Please excuse
Go
me.
ahead.
I know nothing about the subject. So, but just to ask you, so even if we fix psi naught and psi, the final state, you know, usually, I mean, there's a canonical set of gates out of which you can build all gates, right? Like in
Right.
the standard sort of non-quantum standard computing. And so that's also the case in quantum computers, right? You have the analog gates. So even after fixing psi naught and psi, is it the case that there's a lot of ambiguity on what complexity you would assign the comparison between the two, going from psi naught to psi?
I would say yes, in that, I mean, you can see it in the discussions of, well, you can see it in the computer science, or not the computer science, the quantum information theorists. I mean, you know, for them, different gates, it may be, in a given experimental setup, different kinds of gates may be easier or harder to build. And so they may choose to work with different universal gate sets. Okay. That's really an aside for us. You know, there's really a question as to what are the, you know, that is a research question in this context of holographic complexity. What are really the gates that we're using to build up these states? And so I would say there's still an ambiguity there.
Okay.
And I would really say that yeah, I would emphasize this point here that you really want to identify universal behavior or robust questions
Yeah.
for this to be a useful diagnostic.
Okay. Thank you.
I think there's another question.
Yes, I have a question.
Yeah.
Yeah, am I audible?
Yes, you are.
Yes, yes, sir. So are the different ways to which we can reach the target state? Can they be weighed by some factor?
Can they be weighed by some factor? I think maybe what you're suggesting is the idea that, well, I've proposed a particular definition of complexity, and I'm guessing, but I'll try. That you're saying, well, there may be many different circuits by which I can produce this transformation or this build the desired target state. And should I give, I've given primacy to the optimal circuit or the circuit with the minimum number of gates. Is there a way in which I can, give some kind of average complexity by thinking about lots of different circuits, or well, more than just this optimal circuit? I guess there is a proposal where one can think about that. I'm not sure how you would, well, I don't know what exactly the rules would be, in that I can, given, if I give you a particular circuit here, I can always apply a gate and then apply the inverse gate an arbitrary number of times. And somehow, I think we all would agree that's just something trivial, and that, that shouldn't somehow affect the complexity of this particular task. So there may be a slightly different set of rules. This is one simple set of rules. It's one that's very close to what's used in that we've inherited or we're borrowing from our friends in computer science and in quantum information. When we come to holographic complexity, it could be that this isn't the precise rule that we want to use. I'm not sure if that answered the question or not.
Yes, sir. It kind of did.
Okay. And
Sir,
there's
I had one more question regarding this, sir.
Okay, sure.
So can we define complexity as the path with the lowest distance on the unitary manifold? And in that case, would just adding gates to a final state reach the same? Would it reach the target state in the minimum number of gates? Would that, I mean, like, if you have started with psi naught and we want to reach a target state, and we have reached 1 minus the target state, and we finally add a gate to the target state, but it can also be that final path which we have taken from psi naught to the final state is not actually the shortest path because of the curvature of the unitary manifold.
So we're really getting off into topics that we're not going to be the focus of my talk today, but so yes, well, there's several interesting things in there. Yes, you could use sort of distances with some conventional or some metric on the unitary manifold. You don't want to use the standard metric and allow for arbitrary trajectories or geodesics on that manifold. That somehow gives a trivial definition of complexity, and it doesn't correspond to what I'm talking about here, in that it allows for, if you like, arbitrary gates, arbitrarily complicated gates to be implemented with the same cost as very simple gates in other cases. And so what you really want to do is have a restricted, or you want to create a more interesting metric on that space. And it's one that really emphasizes the easy directions or the particular directions that you can move using these so-called simple gates. And so that's, really a geometric approach that was advocated by Mike Nielsen, and I and others have also adopted that and tried to implement it in the context of building quantum states. But again, it's really not the topic of today's talk, but maybe we can talk afterwards if you have other questions about that. There's one more question, and I'll take that if it's a short question, but I feel I'm getting derailed here, but let's have this next question.
Yeah, it's a short question.
Sure.
The thing is whether there is a quantum field theoretic formulation of the problem, in the sense that you can always go from one state to another by the action of some sort of creation annihilation operators. So has anyone tried to do it that way? That's the question.
Certainly, again, that's something that various collaborators and I have tried, and various other groups have also been looking at that. There's in fact, just in the past year, there's a lot of, there've been some interesting studies looking at using, Virasoro algebra or using, various well, that's not directly what you were referring to, but in conformal field theory, using various conformal operators to generate orbits or to construct states. So there is, again, a fair amount of work in that direction. It's not a final, I don't think there's a final, manifesto or a textbook answer yet on how we should implement this in quantum field theory, but there's certainly been a lot of interest in trying to work in that direction.
Okay, thanks.
But I really wanted to focus on the geometric picture today, and so as well as making the suggestion that we should think about holographic complexity, Lenny also made two proposals as to how we should evaluate the complexity in the context of holography. And so the first of these is complexity equals volume. And so the idea is I'm thinking about a particular quantum state in my, so here I've got my black hole, and I'm thinking about the state that's defined on these two time slices in the asymptotic boundary. And what he said is, well, we should do something where we think about all Cauchy surfaces or codimension-one surfaces that join those two boundary slices. Just as in the Ryu-Takanagi proposal, what we do is we then maximize the volume of this codimension-one slice, and that picks out a special slice, and its volume then would give us a measure of the complexity of that state. Alternatively, afterwards, he came up with the idea of complexity equals action, where what I'm doing is I'm taking this Cauchy slice or a Cauchy slice that is anchored on our boundary time slices. And then I look at the domain of dependence of that Cauchy slice, and that gives me a region of the space-time in pink here. It's often called the Wheeler-DeWitt patch. And what one does is evaluates the action on this particular region of space-time. And again, the proposal is that quantity will give us a measure of the complexity of the state. One of the things that's true by construction for both of these new observables is that they probe the interior of the black hole, and they do so at arbitrarily late times, i.e. as I push T left and T right up and up further in the diagram, there's no sense in which they snap back and only probe the interior, as we saw with entanglement entropy. Rather, they continue to probe the interior of the black hole geometry.
Sorry, Rob, can I ask a
I'll also, can I add one more thing and then have the question? So the one more thing is that there was also another proposal by our friends in Texas, and what they said is just, rather than evaluating the action on this region of space-time on the Wheeler-DeWitt patch, we can just evaluate a simpler quantity, namely the space-time volume, and that also should give us a measure of complexity. But there was a question. Go ahead.
Yeah, this is a very basic question. I mean, when you say volume, this is the volume of the same type of, same codimension slice as the Ryuta-Yanagi surface. Then
no, a Ryuta-Yanagi surface is actually a codimension-2 surface. So if we go back to the pictures for a moment here, so this green surface is like the kind of surface that we're interested in. It's a codimension-1 surface. The Ryuta-Yanagi surface is sort of this line inside of that, and it's actually a codimension-2 surface in the whole space-time. So when we move to complexity equals volume, we're moving to a higher dimensional surface. It's a Cauchy slice, or provides a Cauchy slice here, and it's a codimension-1 surface. And also, this is actually a whole region of space-time, so that's a codimension-zero region. Sorry, go ahead.
Why should the volume be bounded from above? I mean, why wouldn't there be like short distance wiggles in the volume?
Oh, I mean, it's really because of the signature of the space-time. This is a Lorentzian space-time. And so on my picture, if I push the surface up here, you may think, well, on the picture, if I put a little dimple there, I don't know, I can't do it, but it may look like the surface is longer, but because you've actually pushed it in a time-like direction, it turns out that the volume is smaller. So it's really the space-time signature that suggests that we should look for a maximum.
Okay, thank you.
Sorry, Rob, not to slow you down.
No, go ahead.
Just very quickly, L for the left-hand side proposal then is the length of the perimeter, or more generally the area of the perimeter. Is that right?
I was going to make a brief comment on that.
Okay.
L. So on this side here, when I'm doing complexity equals action, I don't need any extra, this is just a dimensionless quantity, and so I'm happy. On this side, if I take the volume, it's natural to stick in Newton's constant, but the dimensions here don't match. And so we have to introduce some extra not time scale. We have to introduce some extra length scale, and that's just this L. Typically, when we do calculations, what we choose is the curvature scale of our ADS space.
I see.
But I've just left it as an L here to emphasize that it's really an arbitrary choice we get to make. Okay. There isn't a at present there's no argument that clearly selects out a particular scale that I have to stick into that formula.
Okay. Thank you.
Okay.
Yeah, Rob, can I ask?
Yeah.
So these different definitions in the bulk, do they reflect the different possible notions of complexity in the quantum theory?
Well, that's what I'm going to say in a number of slides. But yeah, it seems very natural that, well, there are all these different, there are a number of different proposals here for complexity. Isn't there, when it comes to entanglement entropy, there's one formula and it's the right answer, we know, or we believe. Here, there are a number of different proposals, and they all, have different advocates. and I haven't really explained why yet, but you know, any one of them may behave, or they all seem to behave in a way that we can associate with complexity. And so it's very natural to think that, well, perhaps that's associated with the ambiguities that I talked about when we try and define complexity in a microscopic way in working directly with the quantum state.
Okay, thank you.
But I really should have answered first now the question, well, these are nice geometric observables in our, you know, new probes of our space-time, but why should I associate them with complexity? Well, there are a number of different reasons. The first one has to do with something called the multi-scale entanglement renormalization ansatz, which is really a way that the condensed matter physicists have come up with to represent quantum states. So the idea here is I have some spin chain and I'm looking for the ground state of some complicated Hamiltonian. And it turns out an interesting or an efficient way to organize our representation of that state is through a tensor network that has this structure here. And I'm not going to go into the details of it, but it's called a Mira tensor network. But this is actually a quantum circuit. Each one of these blobs or tensors is actually a unitary, and you can imagine that what it's doing, say at this state here, is that this unitary is bringing in rather a reference bit that's just in some down state, and it's mixing it with some input from the rest of the circuit here, and it's building up. Then it's entangling that extra qubit or extra bit in with the rest of the system. And so this really is, you can think of it as a quantum circuit that takes us from a simple reference state of unentangled qubits down to the desired, well, qubits or spins down to the desired ground state wave function down here. So that's very interesting. The reason it comes up in the holographic discussions is that Brian Swingle realized that there's actually a hyperbolic geometry hidden in this circuit. And he made arguments for a proposal where he related this geometry or this tensor network to the geometry of the time slice of anti-de Sitter space. And so if complexity is counting the number of gates in the circuit, what I'm doing by when I connect that with Brian's ADS Mira proposal is that counting the number of gates is really just counting or evaluating the volume of this time slice. And so that looks very much like this complexity equals volume prescription. And so that was argued to be, that was given as an argument in favor of thinking about this particular proposal here. Another result is that if I look at either of these proposals, what you'll find is that at very late times, well, also at high temperatures, when I'm pushing this, you know, these boundary slices to late times, that the time rate of change of the complexity is actually proportional to the mass of the black hole or the energy of the system. Now, why does that, well, vote in favor of this being complexity? Well, you can think of the boundary theory, and there you have a very large number of degrees of freedom and a spectrum that's very random. And it was argued by Lenny and friends that, you know, for a very long time in that kind of system, you should expect the complexity grows linearly in time. And the idea is basically that you have this complicated state, and the time evolution is basically just applying gates at random to that state, and it's making a more and more complex state. And it would be very, very exceptional if a gate, you know, was acting at a particular place in my you know, amongst my degrees of freedom, and it caused a cancellation, i.e. it reduced the complexity of the state. And so it was, well, so Lenny's argument is it should grow linearly in time. What should the coefficient be? Well, it should be proportional to the number of degrees of freedom. The entropy of the thermofield double state is a proxy for the number of degrees of freedom that are relevant in that particular state. But I'm thinking about a time rate of change, and so I need another scale to make up the dimensions, and the temperature is the natural scale to introduce there. And so what you expect is then that the time rate of change would be proportional to the entropy times the temperature. But in a conformal field theory, that is precisely, well, that itself up to some factor is equal to the mass of the system. And so just a very qualitative argument says then that in these systems, you should see a linear growth proportional to the mass. I wanted to add, though, that this is part of a much bigger story where eventually you would see the complexity saturate at a very large time scale. There'd be a long time in which there were small fluctuations, but it was essentially saturated. And eventually you might see Poincare recurrences. I'm just going to be talking in today's talk about this part of the evolution. There's an interesting paper recently by these folks where they argued that replica wormholes or topology change might actually be give a geometric realization to see this kind of saturation here at very late times. But I'm not really going to touch on that today. Again, I'm just talking about this quote unquote early time phase. And the last idea that was argued for was the switchback effect. And so this is an interesting idea. Here I'm going to take my thermofield double state and I'm going to involve it in time, but I'm also going to perturb the system. I'm going to hit it with some operator W at different times along the way. And in fact, I'm not going to do this in the usual way we would, where T1 comes first, T2 second, et cetera, et cetera. Rather, we're going to do this, or the idea is to think about it in the context where these times appear in a zigzag order. So T1 is early, T2 is later, T3 is earlier again, T4 later, as I've drawn here in this particular picture. Now, what we argued for a couple slides ago was that as we were evolving in time, the state should be becoming more complex. And so I should see a growth in the complexity that's proportional to, the lengths of all of these intervals. But what one can argue for is that there should be sort of a time delay or a subtraction that I have to make. And the idea is that, if we focus our attention here on T3, if there was no operator there, I could evolve backwards in time and then forwards in time. But the backwards and forwards evolution would precisely cancel out. And so there wouldn't be any increase in the complexity associated with this so-called fold in the time trajectory. Now, if I have a small operator that doesn't create a large disturbance, but say acts on a few number of degrees of freedom, well, in this vicinity, that operator doesn't have much of an effect, and so there would be a partial cancellation. However, the effect of that operator would eventually grow and spread throughout the entire system. And so at that point, you wouldn't see this kind of cancellation. And so the idea is that this subtraction is a universal behavior, and it's reflecting the fact that there's a partial cancellation of the forward and backwards time evolution or in the complexity while the operator is sort of being mixed in or is scrambling, its effect is spreading throughout the entire system. Okay, so I can describe that formula as this is the total time in the whole trajectory, and then I'm subtracting off for each fold, each one of these zigzags, I'm subtracting off a scrambling time, which reflects this partial cancellation in the evolution of the state. And then I'm not going to go into any of the details, but one can think of these probes as being shock waves or null wave shells that we're probing the black hole geometry with. And if you look at, say, in this picture, the complexity equals volume proposal, what you'll find is that you'll get a formula that's very much like this, that there is the expected growth associated with introducing these probes, but that there is this partial cancellation reflecting the switchback effect. And so those are the arguments that were proposed, or they're, qualitative, at least, arguments in favor of these new gravitational observables, giving us a measure of the complexity of the boundary state.
Sorry,
sure.
Excuse me. I missed that. Both the proposals have this time delay in them then, or is it only one or the other?
No, it's in fact, all three of these proposals have the late time of growth being proportional to the mass, and they exhibit the switchback effect.
Okay, thank you.
The picture I showed you was a picture talking about complexity equals volume, but you can also think about complexity equals action, and you get more or less the same result.
I see. Okay, thanks a lot.
Or complexity equals space-time volume.
Nice.
So here we have these various proposals. Where did they come from? Well, they were really, at some level, rabbits pulled out of a magician's hat. But they satisfy these qualitative features. I wanted to add, I mentioned the scale here in complexity equals volume. A similar scale here appears in complexity equals space-time volume. And in fact, there are similar complex ambiguities that appear here in the boundary terms needed to define the action on this region, in particular associated with boundary terms on the null surfaces here. But as Gautam was saying, well, perhaps all of these ambiguities and these different proposals are related or connect nicely with the original discussion I had of complexity, where there was, it seemed, inherently a number of ambiguities just arising in discussions of complexity. Now, actually, because time is short, I'm going to skip through this because it ends with a big X on it. But that was just a motivation for us to do the following. So,
Rob, we are very sorry to say we are very relaxed about time. If you have
okay, okay, okay. In that case,
yeah,
I'll spend some extra time then here.
In fact, no seminar has ever finished on time. So 1.5 hours is the minimum. You can take it.
Sorry. Oh, really? 1.5 hours is now my minimum. Okay. I'll rise to the challenge, although at 2 hours I have to be in another meeting, unfortunately. So okay. So this actually, this is really an aside, but it is it was discussing these results, which I got with two of my students, or they're postdocs now, but they were my students last year, to think about complexity equals volume, or holographic complexity in a more general context. And in particular, it came out of thinking about quantum extremal islands and doubly holographic models, but that context isn't so important here. What I'm going to do is I'm going to remind you about gravitational entropy, which Wald first thought about for black holes in the context of higher curvature gravity, and Dong later thought about it in the context of holographic entanglement entropy, again, in the context of higher curvature gravity. And so what Bob told us is that, well, if I'm given some action with, say, an R squared term in it, or higher powers of curvatures, the natural thing, or the thing that I should do to evaluate the horizon entropy of black holes in that theory is I should think about a formula like this, where what I'm doing is I'm taking a variation of the Lagrangian, or the action with respect to the curvature. This will give me some expression, which in the case of Einstein gravity reduces to just the area of the horizon. Actually, it gives me precise, with those that normalization gives me A over 4G. But if there were higher curvature terms in the action, it would also give me terms involving integrals of curvatures over the horizon. What Zhidong showed was that, what we showed earlier was that was not enough in the case of holographic entanglement entropy. And it amounts to the fact that really what Bob was talking about were stationary black hole horizons, which are, have some extra properties. In particular, the extrinsic curvatures of those surfaces vanishes. What Xi came up with was a formula to account for the extrinsic curvature in surfaces where it was non-vanishing. In particular, the extremal surfaces that we think about in holographic entanglement entropy have a vanishing of the trace of the extrinsic curvature, but not the full extrinsic curvature tensor does not vanish. In any event, that was a lot of words. What Xi said is, well, we should enhance Bob's formula by having a contribution here that involved a higher order variation of the action, and it also involves various extrinsic curvatures evaluated on the surface. Now, what we were thinking about was complexity equals volume and how that might generalize in higher curvature theories of gravity. And in fact, these doubly holographic models gave us a prescription by which in a particular context, you could calculate both what the higher curvature corrections to the action were, and also what the higher curvature corrections to the volume were. And we came up with a proposal that looks very much like this Wald-Dong entropy proposal. So there's a first term here that involves just a variation of the action with respect to the curvatures. These normalizations are all chosen so that at the end of the day, that ends up being the volume over G Newton. Or, well, I guess I've extracted G Newton. This just ends up being the volume of my codimension-one surface for Einstein gravity. But if there are higher curvature terms, I get higher curvature, or I get powers of curvature. And in general, the extrinsic curvature is not vanishing. And so there are also corrections involving extrinsic curvatures appearing on the surface. And so here's a simple example, which actually comes from our doubly holographic model, but I have a gravity action that has a cosmological constant, an Einstein term, and then a certain curvature squared term that we can calculate. And it turns out that the generalization of complexity equals volume, well, it has the volume term, but then there are these corrections that involve here the extrinsic curvature and here a single power of the curvature, the background curvature integrated now on my extremal surface. So that got us thinking that it may be interesting in various contexts to be thinking about not just the the volume of a codimension-one surface, but adding various curvature terms or curvature corrections. But that was all motivated by the idea that I'm thinking about more complicated theories of gravity. And that's not what I want to do today. What I want to do today is just think about Einstein gravity. But what I'm going to do is I'm going to think about what does complexity equals volume really entail. And I'll claim that there are actually two steps here in this formula. The first step is this maximization. And what that's doing is it's, you know, I've got my two anchoring surfaces here on the asymptotic boundary. But what the maximization does is it selects out a very special surface here that connects those two anchor points or surfaces. And then what the second step is really is, well, having identified that surface, I then evaluate some geometric feature of that surface. And what that does is it gives me a nice geometric or a diffeomorphism invariant observable that I can assign to my space-time and that I can associate with these time slices in the boundary theory. So let's do that, but let's generalize that two-step process. So the first step we wanted to do was we wanted to find a very special surface, or we wanted to identify a surface in the bulk associated with our boundary time slices. And so I'll just say that what we're going to do is we're going to have some functional of the background geometry and my embedding function, or the position of my codimension-one surface. And I'm just going to extremize over the embedding function or over the position of my surface. And in making this extremization with this general functional, as long as this is a scalar, I've identified a special surface here in a diffeomorphism invariant way. Mm-hmm. But having identified my surface, I can then evaluate various features, geometric features of that surface. And so what I'm going to do again is build a scalar function of the background geometry and my embedding function. And I'm just going to integrate that now on this surface. And that's an operator, or that's an observable that I can associate. It's a number that I can associate with that particular surface. And as I said, that's a very, well, it's a nice observable that I can associate, or I can use as a diagnostic of my space-time. And so what I've done is I've taken complexity equals volume, and I've basically broken it, or I've generalized it in an interesting way. If this was a 1 and this was a 1, I'd just be extremizing the volume, and then I'd just be evaluating the volume. And so I would call that would be my complexity equals volume proposal. But here we've got two different functions in general, and we're evaluating, very different kinds of observables. But, that's very nice from a geometric point of view. Why do we really care? So what? Well, the so what is that, in fact, one can look at very general classes of observables this way, and you can show that, in fact, at late times in my thermofield double state, they grow linearly with time. And in fact, that the constant of proportionality here is proportional to the mass. And further, you can show that, if you think about not just the black hole, but the black hole with shock waves in it, that in fact, these observables illustrate or exhibit the switchback effect. And so what that means is that this very broad class of observables seems to behave just as well as complexity equals volume, and any one of them could be a good candidate for holographic complexity. Now,
Rob, sorry.
Yeah.
Quick question.
Sure.
Perhaps I missed this, but are you choosing your special surface by extremizing the quantity you're going to calculate on that surface? Or is the choice of surface and extremization of that quantity allowed to be two separate things?
In general, these two functions, there's an F2 and an F1, and the subscripts are indicating that these do not have to be the same function. I want them to be nice scalar functions so that this is diffeomorphism invariant and that's diffeomorphism invariant. But in general, you do not have to set them equal to one another. And these two properties still apply.
Thank you.
I have a question.
Sure.
So this holographic complexity, is it supposed to be related to the complexity of the theory on the boundary, or is it an independent object?
Yeah, no. Well, this. Well, I'm not going to go all the way back, but the idea is that I'm using the usual ADS CFT. So I have the bulk gravity theory. I've got a boundary theory for the black hole. I've actually got two copies of the boundary theory. And so the proposal is I'm creating these diagnostics of the geometry that are associated with time slices of the boundary theory. And the proposal is that these geometric diagnostics are giving us an evaluation of the complexity of the boundary state on those time slices. So I'm imagining there's a CFT state associated with this time slice that's given by T left and T right, and I'm evaluating the complexity of that particular quantum field theory state. Is that clear?
Yeah, so in that case, the complexity of the boundary theory is something unique. So shouldn't you be concentrating on whether the bulk theory that you're computing the complexity with is giving that particular complexity of the boundary theory?
Well, no, what I tried to say very early on in the talk was that when we think about complexity, I talked about a very general definition, when thinking about complexity, say, of spin chains. And in fact, it is not a unique quantity. I mean, we can each make our own definitions of complexity and we'll each get, numbers. The precise details of the numbers are, in fact, not the same. But, what you hope is that there are robust features, robust or questions that we can ask of the complexity so that your set of numbers displays a certain kind of behavior and that my set of numbers also display, the same universal behavior. And so the argument that I made was that these kinds of behaviors are in fact robust. What we saw is that there were at least 3 proposals for holographic complexity where we found that the late time growth of this thermofield double state was linear in time, and that this proportionality constant was given by the mass. And then they also exhibited this switchback effect. And so what I'm saying now is that, in fact, those 3 proposals, well, I haven't said it quite yet, but those 3 proposals all fit in a much bigger framework where there's, in fact, a lot of different possibilities that one can study or examine in the bulk, and they're all exhibiting the same universal behavior. And hence my comment that any one of them may be a good proposal to give us a diagnostic of the complexity of the boundary state. Okay.
Yeah.
Well, since I have another hour to go,
Sure.
I don't. But I wanted to just show a simple example. And so in this particular case,
very sorry to interrupt you, but just to ask you, and you can come back to this at the end, or not at all, if you like. But what's the signature of the singularity in any one of these notions of complexity?
That's a great question, and you should ask me at the end of the talk.
All right. Okay. Thank you.
In this example, I'm gonna simplify it. I'm actually gonna make these two functions the same, i.e., I'm gonna extremize the same thing that I'm gonna evaluate at the end of the day.
Okay.
And it's gonna take a simple form here. With the one, I'd just be thinking about complexity equals volume, but I'm gonna add this correction term that's proportional to the Weyl tensor squared. And so I'm going to probe the ADS black hole, a planar ADS black hole, one of our favorite geometries. So here's the metric, but I'm noting here that I'm going to work with it in Eddington-Finkelstein coordinates. And so rather than the usual time slices, I'm thinking about these null time slices. So V equals a constant is a null slice like this, and progressing in V is going forward or up diagonally in the diagram. R behaves in the usual way. I didn't touch that. And here's my blackening factor. So there's a horizon at R equals RH. The vertical lines, of course, are R equals infinity, and then the two singularities at R equals 0. As I was saying, I want to think about the quantum state given, I'm specifying two boundary times, and I'm thinking about the boundary state there. For simplicity, I'm going to set those two times equal to some time parameter over 2, and I'm sticking in the 2 just so that in my formula here, I just get an e to the tau, e to the I tau up there. And so what we want to think about are extremal surfaces, things that extremize this functional and stretch between my two boundary time slices. And then we'll be thinking about pushing those time slices up on both sides of the diagram and probing further into the geometry. So I can take that functional and I stick it in, or I take this and I just stick it in. I evaluate it for the particular black hole geometry, and I get an expression that looks like this. There's some measure factor, a power of R. There's this factor, which is really giving me the 1 plus c squared, and it evaluates to something like this. There's the 1, and then there's again some power of R, or it's actually RH, the horizon position over R to some power. And I've shifted the coupling just to reduce the clutter. And then this is really what's telling me where the surface is. It tells me how the surface moves. I've introduced some function sigma, a coordinate on a radial coordinate on my surfaces, and then I'm imagining that V and R are functions of that particular world volume coordinate. So one of the things I get to do is I get to gauge fix. In this formula, you can see that if you can reparameterize that sigma in many different ways, and it leaves the answer invariant. So a convenient way to gauge fix is actually to take this expression here and equate it to A and this power of R that appear. And the facility of that will become apparent in a moment. But first, I wanted to say that, as is usual in holographic entanglement entropy or in holographic complexity, I think of this, quantity. This is my integral over the surface of my function, and there's a square root of h in there as well. But I think of that as an action, and so this is I can think of as a Lagrangian. Hamilton-Jacobi, that gives me some intuition for the system. And what Hamilton-Jacobi tells me is that the time rate of change, if I evaluate this on shell, I evaluate the on-shell action, the time rate of change is given by a particular momentum associated with, well, here I've got the velocity in time. And so this is a particular, well, this is just borrowing some formulas out of a classical mechanics textbook. But I also want to say that in this geometry, time and v asymptotically on the asymptotic boundary, oh, that should have been at the, well, there should have been, well, this is actually in the asymptotic boundary, so infinite sigma. The time and the v coordinate coincide there. And so I can also think about this as the momentum in v. Now, the reason I draw our attention to that is, well, okay, one, it's telling me about the time rate of change of this quantity, which we're going to be interested in. But here I've associated with the v momentum. And just by looking at that Lagrangian, we can see that it doesn't depend on v explicitly, and so that's actually a conserved momentum. And my claim is that it takes this simple form here, which is probably simpler than you expected, but in fact, that was the facility of this gauge fixing condition. That if I evaluate p sub v, or this variation with respect to v dot, I get a slightly more complicated expression, but then when I substitute in this gauge fixing condition, it just reduces to this very simple expression here. And in fact, given that gauge fixing condition and given the conserved momentum, I can actually solve both for v and r. Those are what I have are two first order equations in the two unknowns. And in fact, it reduces down to solving a classical mechanics problem of the following form. So I have my r dot squared, my kinetic term. I've got an effective potential, and then I've got an effective energy that's proportional to this conserved momentum squared. And the potential is just this factor here. So it's got my blackening factor in it. So this potential vanishes at the horizon, and then it's got this extra factor that told me about my function, and it's got this measure factor, some power of r. Well, it's actually, those are squared, but. So now I have a very simple, again, intuitive picture on how to solve for this surface. And here what I've done is a typical potential. And so in fact, if I set lambda to 0 and I was just thinking about complexity equals volume, I would get this black line. And so there's this peak. It goes to 0 at the horizon, and then it dives down to minus infinity. When I add this correction term, well, it modifies the potential slightly. It's still diving down to infinity over here. There's the peak, it dips down, but then as I approach r equals 0, this factor takes off. And in fact, now the potential shoots up to plus infinity. You can evaluate the position of this peak. And in fact, well, that, if I'm thinking about a trajectory, that a possibility, again, I'm just solving this for this classical mechanics problem. A possibility is that I just sit at the top of the peak and I don't go anywhere. So r dot squared is equal to infinity. And in that case, then what I have is that the PV at this particular point, that's going to be a special value, is equal to the potential at the stationary point. And it turns out that if you go through all the math, that's just proportional to this power of the position of the horizon. But that, it turns out, is precisely the mass squared. And so we'll see in a moment that, you know, what we saw is the time rate of change was proportional. The time rate of change of our new quantity, our generalized volume, was proportional to PV. This is going to be a very special value of PV, But what we see is that it's proportional to the mass. So in general, though, what I've solved for is the radial profile. What I also have to do is I have to figure out, well, where do these surfaces attach to the boundary? So I've got profiles, or what I'm imagining is I have a trajectory that starts out at infinity, it comes in, it hits the potential, and then it bounces and goes back out. So it comes into a minimum radius and then it heads back out.
Rob, can I ask a question?
Yeah.
So here you have taken, I presume, lambda to be positive, and I'm curious what would have happened if lambda was negative. I presume that's something, or would that make a difference?
In fact, yeah. I've been a little bit bold and glib in what I've said before. We're going to have some restrictions on the values of lambda.
Yeah.
But, here what I've done, I can see that the peak moved up. And so you're right. I assume that lambda was positive. If lambda was negative, it would just drag the peak down. But it really doesn't change the essential features of the story if it's negative.
Nice.
But again, the kind of trajectories that we're thinking about are these where I've got, a particular value of PV. And so that characterizes an energy. I come in, I bounce off the potential, and then I head back out. And so in this diagram, you can see that, I start at large radius, I move in, I reach some minimum radius, and then I go out again to very large radius. But given a particular value of PV or a particular trajectory, I want to know what was the boundary time. And so I have to do some integral here. And what you find is a result like this. So these are different values of PV, and these are the boundary times. And so there are actually two different branches. But this red branch, what it corresponds to is, well, if I set PV equals 0, I see that tau equals 0. So that's just the usual, or it's just this t equals 0 slice. It runs down to the bifurcation surface and then heads out again. As I start to make PV bigger, I'm moving up. And I'm getting surfaces like this. Eventually, what I get is a surface that sort of hugs this critical value of RF. Remember that was the position of the peak here. And then at very late times, it heads out again and connects out to the boundary. And so that's what's happening on this red branch. But I can actually go to larger values of PV. And what we see there is, well, if I'm at a larger value of PV, I come in, I pass over the peak, but I hit the potential at some position much closer to the R equals 0 or much closer to the singularity, and then I head out again. And so what happens on the blue branch is that you get surfaces like this. They're coming in, they're following more or less the same trajectory, but then they head in closer to the singularity, come out. And what you're doing as you increase PV here is you're going from surfaces up near the singularity down towards this blue surface that happens to be connected to t equals infinity. But in fact, you can keep going and you'll end up with you'll end up evaluating this integral and you'll get a negative value of tau. And so you're actually connecting to the boundary down here. Now, an interesting thing is that there's a time reflection in the geometry that wasn't immediately apparent, or it was not apparent in the V coordinates that we used. And so I can take that surface with negative time and I can think of it as a surface for positive time, except that it goes backwards and probes the white hole geometry region like that. So for any given time slice here, there's actually a family of different surfaces, extremal surfaces, there's this more or less straight one, and then there's one that probes towards the future singularity and one that probes towards the past singularity. But we have to ask, what was the maximum? What was the maximum one? Because that's the one that we imagine is going to be the useful diagnostic of complexity. It turns out that this red branch, or these surfaces that are, smoothest, or in this picture, I said flat, those turn out to be the global maximum. And so they're the ones that are going to tell us about the complexity. As I said before, in this particular case, when we think about the time rate of change, it's proportional to this PV. But in particular, you can see that something special is happening here. The time is running up to very large values, but PV is not changing very much. And that's because you're looking at these trajectories that are getting, very close to the peak and then bouncing off. And so they spend a lot of time near the peak of that potential. And so at late times to leading order, these are all proportional to that P infinity, which I argued was proportional to the mass. And so you're getting the behavior that you expected. In fact, you see it's also true on this other side. But for the global maximum for the red curves, I get this desired behavior that the late time rate of change is proportional to the mass. You can also think about the switchback effect. It's more involved, and you have to look at curvatures or in detail at the metric. But essentially what it amounts to is you have to worry about whether there were any delta function contributions near the shock waves. And it turns out the answer to that question is no. And so it turns out then that, this new observable also satisfies or exhibits the switchback effect. Gautam asked about being negative. And well, what I should have said is that, lambda can take a range, but it can't be too large. You want there to be a maximum, and you want there to be a maximum behind the horizon. And so it turns out that this lambda parameter, or the one that I've shifted by powers of the boundary dimension, can sit in this range. And that guarantees this kind of behavior, that there's a maximum in the potential behind the horizon. And all of those potentials, all of those observables show this kind of behavior, namely late time growth that's proportional to the mass and the switchback effect. A side comment is that we also have these extra extremal surfaces. We don't see an obvious role for them, but it's intriguing that they actually probe near the singularity, and perhaps there's a role for those when we fully understand holographic complexity. Well, I'll take a few more minutes. What I talked about was generalizing complexity equals volume so far, but what about complexity equals action, complexity equals space-time volume, where what I'm doing is I'm evaluating various quantities on the Wheeler-DeWitt patch. Here, didn't seem that there was any kind of extremization procedure. We just had these null surfaces, and that bounded some nice domain or region, space-time region, a codimension-zero region. And they both provide a nice diffeomorphism invariant observable. Well, I'm going to change, or I'm going to embellish this program, and I'm going to say, well, we can approach this, the idea of codimension-zero regions in the same way that we did before. And so we'll have two steps. First, we're going to identify a very special set of surfaces that bound a codimension-zero region. And then given that region, we're going to evaluate some nice geometric feature of it. And we could involve boundary terms as we do here for the action. And the idea is that, again, we're producing some nice family of diffeomorphism invariant observables. And so now the equations start to explode. There are all sorts of functionals that we get to choose. There are functionals that we get to choose associated with each of our boundary surfaces. There's a functional that I get to choose with the interior region. And I'm extremizing the embedding functions both for the top and the bottom surfaces. But the idea is that, with a very general procedure like this, I choose a region of the space-time in a diffeomorphism invariant way. One very simple example is you could choose, F6 to be 0, F4 and F5 to be, these functionals that I talked about before, the 1 plus lambda of Weil tensor squared, but I'll change the lambda and so displace those two surfaces slightly. And what that would give me is some very narrow region, but it would pick out a space-time region by choosing these two surfaces in a new way. That's not the example I'm going to talk about in a moment, but that's perhaps a simple thing to think about. And then the idea is, given your space-time region, well, let's start evaluating geometric properties. Again, what I can do is I can build some functional that tells me about the interior here. Or, well, I guess this is the one that tells me about the interior, but I could also add boundary terms that I attach to the top or the bottom surfaces here. And again, with this two-step procedure and now all sorts of functionals or all sorts of possibilities, I pick out a nice diffeomorphism invariant observable. And the claim is that I should say perhaps in some cases, this is very much a work in progress, as designated by the signs here. But we seem to be able to find a large class of observables in this way that again shows this universal behavior that we saw before and argued was something that would characterize diagnostics of the complexity. So in this case, the simple example that I'd like to think about is this. So what I'm extremizing here, or what my functional is I'm going to evaluate here the volume of the top surface, the volume of the bottom surface, and then I've added a term which is just the space-time volume of this intervening surface. And you might note that all of these extra scales I've just set to the ADS curvature scale. The one thing that I did is I added extra coefficients to let me tune the contribution of these two boundary terms in my extremization procedure. It turns out that the equations that extremize the surfaces for this simple example have a well-known, they've been studied before. For example, it was actually only a lecture by Ed Witten. But what the surfaces are now constant mean curvature slices, i.e. they're surfaces where the trace of the extrinsic curvature is not 0, but rather it's given by some constant. And you can see that the constant is given by the ADS scale, and that's really because the relative scale between these coefficients is a power of L. And then there's the, what appears here are these coefficients that appeared in my two boundary terms. So I can choose those alphas. Well, I've assumed that they're positive in this particular case. In order for this to be the top surface and that to be the bottom surface, otherwise it wouldn't make sense. but I can think about the limit where these alphas go to 0. And what that means is that I'm getting a divergent extrinsic curvature. But what that's really meaning is that these surfaces are being pushed up, or this surface is being pushed up, and it's actually becoming a null boundary. And similarly, this one's getting pushed down, and it becomes closer and closer to the null boundary that we saw before for the Wheeler-DeWitt patch. And so in that limit, this procedure then is picking out, the region I'm picking out is precisely the Wheeler-DeWitt patch. And so now I have the liberty, according to this program, of evaluating some other functionals on that particular space-time region. And so in the first case, well, I'm actually using the same functional. I'm just evaluating the space-time volume. That was what we called complexity equals volume 2.0, or complexity equals space-time volume. Another possibility is that what we do is we have, rather than evaluating this functional, we evaluate the action on that particular region, namely on the Wheeler-DeWitt patch, and that's just the complexity equals action procedure. And of course, though we know, I mean, I told you at the beginning that both of these procedures, or both of these prescriptions obey these two universal behaviors that we've seen before. And so it's perhaps not so surprising that these are actually obeyed by a much larger class of observables that you've constructed, or that we've proposed constructing in this particular way here. In any event, that's coming close to an hour and a half, and it brings me to the end of the talk. And so this is just the conclusions. The basic idea is that, we had various discrete possibilities or proposals for diagnostics of boundary complexity. And now what we've shown is that they actually fit in a much broader framework of geometric observables in our holographic space-times. And in fact, this broad family actually satisfies these robust behaviors, which makes them good candidates for holographic complexity. We talked a little bit about, is this new extended freedom that we've talked about related to freedom in constructing complexity at the microscopic level in the boundary theory? Could it be that these, these extremal non-maximal surfaces have a role to play? Because intriguingly, they're probing very near the singularity. It's not just codimension-one, it's also the codimension-zero observables. And so in general, there's lots to explore here. And I guess I should thank you for your attention and for all the questions. But if there are more questions, I'm happy to try them.
Let's first thank Robert for an interesting talk. Questions?
Let me ask one. Robert, sure. As you know, the holographic entanglement entropy obeys many inequalities.
Yeah.
One of the beautiful things about the holographic prescription was that it geometrizes some of these inequalities. And I was wondering whether there were any analogs of those kind of universal inequalities that apply to any suitable definition of complexity, and whether one could see them holographically.
I think the short answer is no. The longer answer is that's a point of frustration. I mean, the beauty of holographic entanglement entropy is that that is a well-studied quantity, and in particular, it was well studied in conformal field theories, at least in 2 dimensions. And so you could actually not just make qualitative comparisons, but you could make quantitative comparisons that, detailed formulas, say, for the entanglement of an interval in a thermal state, that formula matched precisely what you were getting in the holographic picture. Unfortunately, for complexity, the idea of complexity, in particular complexity in quantum field theory, is a much less studied idea. I think it's actually coming to the fore more, or there are at least some, say, condensed matter physicists I know who are becoming more and more interested in that set of ideas. But we really don't have at this time quantitative points of comparison where I can say, look, here is my here's my calculation in the quantum field theory, here's my calculation on the holographic side, and they match in a way. And I know that's going beyond or asking for more than sort of the inequalities that you were referring to, but at present, I don't think we don't have those either.
Thank you.
Other questions?
Sir, I have a question.
Yeah, please.
Sure.
Yes, sir. In the gauge fixing in the gauge fixing for the external surface, if we include Hawking radiation, will there be any kind of change?
Well, I'll say just generally, I mean, one of the things we've found recently is that, well, one of the things, say in this formula is, it looks very much like a saddle point expression. And the same was true of the Rutak-Yanagi prescription for holographic entanglement entropy. In the case of entanglement entropy, there's been a lot of excitement about including quantum corrections in the bulk, i.e. 1/n² corrections in the boundary theory. And that's led to, or that's been a key in sort of this whole story about quantum extremal surfaces and the page curve and all that. But I have to say that, we're not sure what the corrections, 1/n² corrections to these kinds of saddle point expressions would be at the present time. And in part, that's just reflecting the fact that we don't really have a good handle on what complexity is in a quantum field theory. But it's a great question. But again, it's a point of frustration that we're still working at this very preliminary saddle point, or with these saddle point expressions, large N saddle point expressions for the complexity.
Thank you, sir.
Sorry, Rob, can I ask you a question? This is kind of vague, I apologize, but so, I mean, it seems you have several possible definitions of complexity in the boundary theory, and now you're given a beautiful large class of definitions in the bulk. But I'm wondering whether one could, just using the holographic dictionary, try to map a particular definition of the boundary to the bulk. It sounds ambitious, but just to ask it like this, let's say we start with a state, not a totally disentangled state, which will have some firewalls or something, but some fiducial nice state. And then in the boundary, we go towards another state by applying a bunch of operators which have duals in terms of being sources for bulk fields. And in this way, we build up a state in the bulk. Is there a way to then, relate your various bulk measures to something in the boundary? Okay.
I think the answer to that is yes. I'm not, Well, I'll say two things. One is, we do have, we've now seen there's this big class of geometric observables. I've talked about ambiguities on the microscopic side as well. Is there some way that we can start to, vary, vary through the family of geometric observables and associate that with changing a microscopic model in a particular way? That's a great question, and it's something that I'd like to think about more. I think, I've focused on a very particular element of the story, but I think, a key idea or something you introduced into the discussion is, well, I don't know what an unentangled state is in quantum gravity. Let's start with, one favorite state and evolve it or apply stuff to it and get another state. There are, or in particular, Vijay Balasubramanian's group has had great success in the past year thinking about not really complexity of states, but complexity of operators, and in particular thinking about the complexity of the time evolution operator, and connecting that through Nielsen's geometric formula, and they've been able to actually make progress there, and it seems that is that's a non-geometric discussion, but it seems like that ought to have some nice geometric interpretation, and maybe connect to these discussions here. And I know there are other groups, for example, Michael Heller, and I think Jan de Boer worked on this as well, Joanna Erdminger, where I think that's basically what they're trying to do is build up a dictionary that goes from a microscopic picture of operations, very particular unitaries acting on our state, and geometric deformations on the other side of the holographic dictionary. But it is sort of reshaping or remolding the question slightly from the question I proposed at the very, very beginning, that I was asking about complexity of a particular state in.
Yeah.
So that was a vague question for a vague answer.
No, thank you. Thanks. I know you have to run, and I don't want to hog this, but just your parting thoughts on what you hope to learn or about singularities this way would be great.
Well, I guess, yeah, I mean, one of the great questions is, well, what's going on here at the singularity? There are, in some sense, complexity equals volume is frustrating because it gets hung up on this peak in our potential, and so it gets close to the singularity, but then it stops, and it won't get any closer.
Yeah.
In complexity equals action, clearly the Wheeler-DeWitt patch touches the singularity, but if you're evaluating the space-time volume or the action, it turns out that, well, the volume is just contracting so quickly at the singularity that there's a very small contribution here. And so somehow these probes don't quite do the job that you might hope. There was this intriguing point, I don't know where it was, that there were, other non-extremal but non-maximal surfaces that perhaps go closer to the singularity. In fact, these up here would go very, very close to the singularity. And so it could be in entanglement entropy, or perhaps in entanglement wedgeology. What we found is that those extremal but non-minimal codimension-2 surfaces actually have a role to play. Yeah. And so it may be, that here we have a probe near the singularity. They're not the maximal surfaces, but perhaps they still have some kind of indirect role to play in this. And so they could tell us about physics close to the singularity. I'm not sure if that answered the question, but those are.
I see. Yeah. Okay. Well, thank you. Thank you very much.
Okay.
Okay.
We should stop here and thank the speaker again.
Thanks a lot, Rob, for a great talk, as usual, with your great clarity. Thank you.
Thank you.
Okay. Well, thank you, and stay safe and stay healthy.
Thanks, Rob.
Okay. Take care. Bye-bye.
Bye-bye.